Everything you were taught about the universe, that it's expanding, growing, stretching outward like a balloon, is only half the story. And the half they left out, it's going to end everything. Actually, let me start over. Because the way I just said that doesn't even capture how strange this really is. The universe is not simply growing. It is being pulled apart. Right now. At an accelerating rate. That exists, and that we cannot see, cannot touch, cannot explain, and have no theory that correctly predicts. And the name we gave it, dark energy, is essentially a scientific admission that we ran out of better ideas. By the end of this documentary, you will understand what dark energy is actually doing. Not the textbook version, not the Wikipedia summary, the real, terrifying, mind-reshaping truth that is reshaping everything we thought we knew about the fate of the cosmos. We are going to cover three things specifically: why the word expansion is the wrong word, what happens when dark energy wins, and what the James Webb Space Telescope is finding right now that is sending shockwaves through the entire field of cosmology. And I promise you, you will look at the sky tonight with completely different eyes. Let's start with the lie. Not a malicious lie. An incomplete truth that got repeated so many times it calcified into something we stopped questioning. In 1929, Edwin Hubble sat at the Mount Wilson Observatory in California and made an observation that would rewrite the entire framework of human understanding. By analyzing the light from distant galaxies, specifically the redshift, the stretching of light toward longer wavelengths that happens when a source moves away from you, he established that galaxies were receding from us. And not just from us. From each other. In every direction. The universe, he concluded, was expanding. This was correct. This remains correct. But here is where the incomplete truth crept in. Most people heard expanding universe and built a picture in their heads. Vu tru nu mo de qua bong, vat chat dang di trian ra nguai qua kong john, nu man vo qua motv you know. Galaxies flying outward like shrapnel from an explosion. That picture is wrong in a way that matters enormously. What is actually expanding is not the matter inside the universe. It is space itself. The fabric of space-time is stretching, and galaxies are being carried along for the ride, not because they are moving through space, but because the space between them is growing. This is a distinction most textbooks either skim past or explain so badly that students walk away with the wrong model locked in. And I know the raisin bread analogy. You've heard it, raisins in a rising loaf, each raisin moving away from every other as the bread expands. My first instinct was to use it here. But honestly, I think that analogy does more damage than good. Because the bread has edges. The bread expands into something. The universe does not expand into anything. There is no outside. There is no surrounding space it is filling. The space itself is what is stretching. The raisin bread puts you outside the system, and the moment you imagine yourself outside the universe, you have already made the fundamental error. So expansion is real. But it carries an implicit assumption that there is something driving this expansion, and that something has limits. That gravity will eventually slow things down, and perhaps pull it all back together. For most of the 20th century, the debate was about which scenario would win, an eternal expansion that gradually slows, or a big crunch where gravity reclaims everything. Then, in 1998, two independent research teams changed everything. Saul Perlmutter at Lawrence Berkeley National Laboratory and Brian Schmidt with Adam Rees at Harvard were both studying type Ia supernovae, stellar explosions so consistent in their brightness that astronomers call them standard candles. You can measure how far away they are and how fast the universe was expanding when their light was emitted. Both teams were expecting to confirm that expansion was slowing. Both teams found the opposite. The expansion is accelerating, getting faster. Not slowing down, speeding up. This discovery earned the Nobel Prize in Physics in 2011. And it broke every model that existed at the time. Because here is the thing, if something is accelerating the expansion of space, there must be a force doing that work. Gravity pulls inward. Something else is pushing outward, and pushing harder over time. They called it dark energy. And that name is where the scientific vocabulary quietly confesses its own helplessness. Dark, in physics means, we know it exists because we can see its effects, and we have no idea what it is. And what it is doing is not expansion, in any gentle, orderly sense. It is tearing. The structure of spacetime at the most fundamental level is being pulled apart at an accelerating rate. The difference between expanding and falling apart is not just semantic. It changes every prediction we make about where this ends. And that endpoint, we will get there. But first, let's understand exactly what we are dealing with. The most uncomfortable fact in all of modern physics is this: dark energy makes up 68% of everything the universe contains. Dark matter makes up another 27%. Ordinary matter, every star, every planet, every galaxy, every human being, everything you have ever seen or touched or thought about, accounts for 5%. 5. Everything science has ever studied directly is a rounding error on the cosmic balance sheet. These numbers come from the Planck satellite data, with the 2018 results representing the highest precision measurement of the universe's composition ever achieved. This is not a rough estimate. This is the number. Now, where did the cosmological constant come from? Because this is one of the most extraordinary ironies in the history of science. Albert Einstein, when he wrote his field equations of general relativity in 1915, found that they predicted a dynamic universe, one that was either expanding or contracting. This bothered him deeply, because the consensus at the time was that the universe was static and eternal. So he added a term to his equations, the Greek letter lambda, the cosmological constant, a kind of built-in repulsive force that would counterbalance gravity and keep the universe in equilibrium. When Hubble's observations confirmed that the universe was expanding, Einstein called the cosmological constant his biggest blunder. He removed it. He wanted nothing to do with it. Here is the irony that physicists still savor decades later: lambda came back. Not as a stabilizing force, but as the precise mathematical description of dark energy, the term that quantifies the energy density of empty space that is accelerating the expansion. The equation Einstein wrote when he was wrong turns out to be one of the most accurate descriptions of the universe we have ever produced. His blunder may be his most profound contribution. But here is where it gets genuinely uncomfortable. One of the leading theoretical candidates for what dark energy actually is, physically, mechanically, is the energy of the quantum vacuum. Empty space, in quantum mechanics, is not truly empty. It seethes with virtual particles constantly flickering in and out of existence, borrowing energy from the vacuum for the briefest possible moment before annihilating. This quantum activity should produce a measurable energy density. When physicists calculate that energy density using quantum field theory, they get a number. And when they compare that number to the observed value of dark energy, the value we actually measure, the discrepancy is 10 to the power of 120. I need to pause here because when I first encountered that number, I genuinely could not process it. So let me try to give you some perspective. The number of atoms in the observable universe is roughly 10 to the 80. That means the quantum vacuum energy prediction overshoots the observed value by a factor that makes the number of atoms in the entire universe look like a rounding error. This has been called the vacuum catastrophe and the worst prediction in the history of physics. It is the largest discrepancy between theoretical prediction and experimental observation that science has ever produced. And it has no resolution. Not a partial resolution, no resolution. Not every physicist believes dark energy is the cosmological constant. An alternative called quintessence treats dark energy as a dynamic field, one that can change over time, with different values in different epochs of the universe. This matters because if dark energy is truly constant, its future behavior is predictable. If it is dynamic, the fate of the universe is genuinely open. We do not know which it is. In 2024, the Dark Energy Spectroscopic Instrument, DESI, released preliminary results that gave the first observational hint that dark energy may not be constant. The confidence level was between 2.5 and 3 sigma. In physics, 5 sigma is the threshold for a discovery claim. So this is not confirmation. But it is the first time actual data has leaned, even weakly, in the direction of a dynamic dark energy. The community did not sleep well that week. Let's talk about the Hubble tension. Because this is not just an academic footnote, it is the deepest crack in the foundation of modern cosmology, and it has been widening for years. The Hubble constant, h, is the number that describes how fast the universe is expanding right now, expressed in kilometers per second per megaparsec. Measure it 2 different ways and you should get the same answer. You do not. Method 1, the cosmic microwave background. The CMB is the afterglow of the Big Bang, light that has been traveling since the universe was about 380,000 years old, now stretched into the microwave spectrum and permeating every direction of the sky. By analyzing its subtle temperature fluctuations with extraordinary precision, cosmologists can model the early universe and predict what the expansion rate should be today. That prediction, roughly 67 kilometers per second per megaparsec. Method 2, local measurements. Astronomers use Cepheid variable stars, stars that pulsate at rates directly tied to their luminosity, to establish a cosmic distance ladder. Calibrate nearby Cepheids, use them to calibrate type Ia supernovae, use those supernovae to measure expansion at greater distances. This approach gives roughly 73 kilometers per second per megaparsec. The gap between 67 and 73 is 8 to 9%. That sounds modest until you understand that both measurements have been refined over decades with every systematic error that researchers could identify already accounted for. This is not measurement noise. The statistical significance is high enough that "we made a mistake somewhere" has become an increasingly desperate explanation. Then the James Webb Space Telescope entered the picture. Webb was able to cross-check Cepheid measurements with a precision that the original Hubble Space Telescope could not achieve: sharper resolution, greater infrared sensitivity, better separation of crowded stellar fields. The 2023 results, published by Adam Rees and collaborators, were unambiguous. Webb confirmed the local measurement. H approximately 73. The tension did not go away. It was reinforced with smaller error bars. I want to be honest with you about something here. There is a version of this video where I mention a tension, acknowledge it exists, and move on. But I think that would be a disservice. Because this disagreement is not a footnote. It is the main event. If two rigorously independent methods of measuring the same thing give fundamentally different answers, one of 3 things is true: there is a systematic error we haven't found yet, which grows less likely with every new instrument that confirms the local value; there is new physics operating in the early universe that altered the expansion rate before the CMB was emitted, or the standard model of cosmology is simply incomplete. Option 3 is the one nobody wants to say out loud. But it is on the table. The candidate explanations are fascinating and unsettling in equal measure. Early dark energy models proposed that dark energy was not always negligible in the early universe, that it had a brief period of elevated activity before the CMB epoch that inflated the expansion rate and left a signature invisible to our current CMB analysis. Modified gravity theories suggest that general relativity itself behaves differently on cosmological scales. Interacting dark energy models propose that dark energy and dark matter exchange energy in ways that alter the expansion history. Each of these hypotheses predicts a different eventual fate for the universe. The Hubble tension is not just a measurement puzzle. It is the question that determines which ending we are heading toward. Let's go to one of those endings. The default scenario, the one that falls out of the standard model if dark energy is constant and the universe continues as it currently is, has a name that sounds almost gentle. The Big Freeze. It is anything but. The timeline alone is staggering. The universe is currently 13.8 billion years old. The last stars will exhaust their fuel and go dark in roughly 100 trillion years, that is 10 to the 14th power. Black holes will dominate an empty, cold universe for far longer, slowly evaporating through Hawking radiation over timescales ranging from 10 to the 67th power to 10 to the 100th power years. And then, heat death. Thermodynamic equilibrium. Maximum entropy across a universe that has expanded to a size that makes our current observable universe look like a speck. In this state, there are no temperature gradients. No hot regions and cold regions exchanging energy. Without a temperature gradient, no work can be done. No reactions. No movement. No information processing. No anything. Forever. The second law of thermodynamics is not a suggestion, it is among the most robustly tested principles in all of physics. Entropy increases. It does not decrease. Dark energy accelerates this fate by doing something that sounds paradoxical. It is making our observable universe smaller even as the total universe grows larger. Here is how that works. The universe that we can, in principle, receive signals from, the observable universe, is defined by the distance light has had time to travel since the Big Bang. It is a sphere about 46 billion light-years in radius today. But the accelerating expansion means that galaxies beyond a certain distance are receding faster than light can cross the growing gap. Their light will never reach us. And as expansion accelerates, that threshold creeps closer. Galaxies that are currently visible will eventually cross that horizon and disappear from our observable universe, not because they are destroyed, but because space-time between us is expanding faster than light can traverse it. Billions of years from now, a civilization with our level of technology but living in that era would look out at the sky and see almost nothing. The Milky Way and Andromeda will have merged into one large elliptical galaxy. That collision is scheduled for roughly 4.5 billion years from now, and it is the last merger of its type our local group will ever experience. Every other galaxy will have retreated beyond the horizon. The sky will be almost dark. That future civilization will have no evidence that billions of other galaxies once populated the visible universe. They will have no reason to hypothesize a Big Bang. The entire empirical foundation of modern cosmology will be gone. There is something about that particular thought that I find genuinely difficult to shake. What does it mean for knowledge to be time-limited not by our intelligence, but by the structure of space itself? If the evidence disappears, does the truth disappear with it? I don't have a clean answer. I think it is worth sitting with the discomfort. The thermodynamic inevitability of Big Freeze is profound precisely because it has no drama. No explosion. No moment. Just the slow, patient, inexorable spreading of everything until there is nothing left to spread. Some philosophers argue this is the most disturbing of all possible endings, not because it is violent, but because it has no witness. But let me give you the violent one. Because Big Freeze assumes dark energy stays constant. And the DESI data, combined with some theoretical models, raises the possibility that it does not. If dark energy is phantom energy, with an equation of state parameter W more negative than -1, it strengthens over time. And that leads somewhere far more immediate. Far more personal. Physicists call it the Big Rip. The mechanics work like this. Dark energy, if it grows, eventually surpasses every other force on progressively smaller scales. The sequence proceeds with mathematical precision. First, the gravity holding galaxy clusters together is overwhelmed, clusters dissolve. Then the gravity holding individual galaxies together, galaxies shred. Then the gravitational bonds of star systems, solar systems scatter. Then the electromagnetic bonds holding planets together, planets explode. Then chemical bonds holding molecules together, every molecule destroyed. Then the strong nuclear force holding atomic nuclei together, atoms themselves ripped apart. And then space-time itself reaches a singularity. In 2003, Robert Caldwell and colleagues published a landmark paper modeling this scenario. Their specific timeline, assuming Big Rip arrives roughly 22 billion years from now, 60 million years before the end, the Milky Way is disrupted. 3 months before, the solar system is unbound. 30 minutes before, Earth is pulled apart. And 10 to the negative 19th seconds before, the precision of that number is almost surreal, atomic nuclei are destroyed. That last number is worth dwelling on. 10 to the negative 19th seconds. That is not a long time before the end during which you could, in principle, observe what is happening. That is the end happening simultaneously with the smallest meaningful unit of time. There is no watching it approach. The rip and the end are effectively the same event. The current observational evidence from DESI 2024 gives values for the dark energy equation of state that technically fall in the direction of phantom energy territory, W approximately -0.99, W_A approximately -0.37. The error bars remain large. This is not confirmation of Big Rip. But it is the first dataset with statistical weight that does not rule it out in favor of Big Freeze. The 2025 DESI results are being watched by the cosmology community with an intensity one have rarely seen applied to a data release. I want to be careful here, because there is a version of this that sounds like a disaster movie, and I do not want to make it that. Because if Big Rip is the correct model, what it means is something more profound than spectacle. It means that every structure in the universe, every bond, every connection, every system that holds things together, has a termination date written into the fabric of spacetime itself. Not as an external event that arrives. As a property of the geometry of reality. And I genuinely do not know how to make that feel small or cinematic. I don't think it should. Here is the detail that reshaped my perspective on this. The universe is currently 13.8 billion years old. If Big Rip arrives in 22 billion years, we are not near the end. We are just past the middle. All of cosmic history from the Big Bang to right now, the formation of the first stars, the construction of galaxies, the synthesis of every heavy element, the emergence of life on at least one planet, that entire arc will happen again before the end. We are at the intermission, not the finale. So how did dark energy come to dominate in the first place? It did not always. There is a specific moment in cosmic history, a power shift, and understanding it illuminates everything about where we are now. The universe has passed through three distinct eras. In the beginning, for the first roughly 47,000 years, radiation dominated. Photons and relativistic particles carried the dominant energy density of the cosmos. Then matter took over. Gravity began to pull ordinary and dark matter into structures, decelerating the expansion. For billions of years, the expansion rate was slowing. The universe appeared to be heading, eventually, toward stasis or collapse. Then, approximately 5 billion years ago, when the universe was about 9 billion years old and Earth had not yet formed, dark energy density caught up with matter density and overtook it. Acceleration began. This transition is now called the dark energy era. We live in it. The mechanism behind this transition is almost elegant in its simplicity and deeply unsettling at the same time. Matter density decreases as the universe expands. As volume grows, matter thins out, like gas dispersing in a larger container. Dark energy density, if it is the cosmological constant, does not thin out. It maintains a constant energy per unit volume even as space stretches. So matter simply diluted itself into irrelevance. Dark energy did not grow stronger. Everything else grew weaker relative to it. Physicists call this the coincidence problem, the observation that we happen to live at a time when dark energy and matter density are of comparable magnitude. Slightly earlier in cosmic history, matter dominated completely. In the far future, dark energy will dominate so thoroughly that matter will be cosmologically irrelevant. Why do we find ourselves in this window of relative balance? The honest answer is, we don't know. Some physicists reach for anthropic reasoning. If dark energy had dominated earlier, gravitational collapse, which built stars and galaxies and planets, could not have occurred. No stars means no heavy elements. No heavy elements means no chemistry, no biology, no us. So we observe the value of dark energy that allows our existence because we could not be here to observe any other value. This reasoning is logically valid. It is also, to many physicists, deeply unsatisfying. It explains why we observe this value without explaining why this value exists. The most ambitious attempt to actually explain the value comes from string theory. The mathematics of string theory generates something called the landscape, a theoretical space of approximately 10 to the 500th power possible vacuum states, each with different values of fundamental constants including the cosmological constant. If all of these states are physically realized, if we live in a multiverse where every possible vacuum is instantiated somewhere, then our universe is simply one bubble with the constants that permit observation. I want to be upfront about this. The multiverse is where the boundary between science and speculation becomes genuinely blurry. It is not testable by any experiment currently conceivable. Many physicists find it deeply compelling. Others find it an abandonment of the scientific program. I've gone back and forth on how much weight to give it here. But I think it would be intellectually dishonest not to name it, because some of the most rigorous thinkers in theoretical physics are investing serious energy in these models, even if it makes their colleagues uncomfortable. And James Webb is, quietly, providing the first real observational pressure on these questions. The telescope has found galaxies with the stellar mass of the Milky Way existing only 600 million years after the Big Bang, structures the Standard Model does not predict forming that early. If these observations hold up under further analysis, they suggest dark energy in the early universe behaved differently than the constant we assume today. Every image from Webb is a test of the theory. Webb deserves its own moment here. Because it is not simply a prettier Hubble. It is a fundamentally different instrument operating in a different regime, and what it is revealing is extraordinary. Webb's infrared capability allows it to detect light from galaxies so distant, so far back in time, that their ultraviolet and visible light has been redshifted entirely out of those wavelengths and into the infrared. This means Webb can observe galaxies from less than 500 million years after the Big Bang with a clarity that was simply impossible before. When astronomers published the Lab et al. 2023 paper identifying 6 galaxies with implausibly large stellar masses at very early cosmic times, the reaction in the community was not dismissal, it was genuine alarm. These objects should not exist under current theory. The confirmation work is ongoing. Alternative explanations, active galactic nuclei inflating apparent luminosity, calibration issues, are being systematically investigated. But each new dataset from Webb has, so far, maintained the anomaly rather than resolved it. Simultaneously, Webb is participating directly in the Hubble tension debate. The telescope's confirmation that local H sits near 73 km per second per MPC, independent of the specific calibration choices that critics targeted in earlier work, has made the systematic error explanation increasingly untenable. The tension is real. The question is what it means. Webb is also building a database of type Ia supernovae across a wide range of redshifts, a direct measurement of how expansion rate has changed over cosmic history. The statistical power of this dataset will peak around 2025 to 2026, when there should be enough supernovae to properly constrain the dark energy equation of state parameter W with precision that current instruments cannot match. We are genuinely close to knowing whether dark energy is constant or dynamic. That answer will define cosmology for the next generation. I'll tell you something. I spent 3 hours going through Webb images while writing this section. Not for research. Just because they are extraordinary in a way that hits differently when you understand what you're looking at. There is something important in that, not just about science, but about the act of looking itself. A species built an instrument, put it at the second Lagrange point, and is now reading the universe's autobiography in infrared light. There is no precedent for this in 13.8 billion years of cosmic history. And I think that deserves acknowledgement before we rush to the next data point. But let's push further. Because beyond all the endings, big freeze, big rip, heat death, entropic silence, there is a class of ideas that asks whether ending is even the right concept. And the mathematics here goes somewhere that made me genuinely question my own cognition at 2 in the morning, which is not a time I recommend for this material. Start with the Boltzmann brain. Ludwig Boltzmann, the 19th century physicist who founded statistical mechanics, understood that entropy is a probabilistic concept. Low entropy states can arise spontaneously from high entropy ones, just with extraordinarily low probability. In a universe that persists long enough in a state of maximum entropy, quantum fluctuations will eventually produce any configuration, any arrangement of particles, any structure, however complex. Including, in principle, a fully formed brain with complete false memories of experiencing a coherent universe. The disturbing implication, given sufficient time, such a brain is more likely to arise from a random quantum fluctuation than an entire ordered universe arising from a Big Bang and producing a biological brain through 13.8 billion years of structured evolution. If you are a Boltzmann brain, your sense of having experienced a real history is an illusion, every memory false, every perception fabricated by the fluctuation that created you. The probability of being such a brain, integrated over infinite time, is higher than the probability of being what you think you are. This is not a thought experiment physicists dismiss. It is an active problem in cosmology, a constraint that any successful cosmological model must address by demonstrating it does not predict more Boltzmann brains than ordinary observers. The fact that you are sitting with uncertainty about whether your current experience is real is, in a sense, a feature of taking the physics seriously. Then there is Poincaré recurrence. The French mathematician Henri Poincaré proved that any system with finite energy and finite volume must, given enough time, return arbitrarily close to any previous state. Applied to the universe, this means, after heat death, after the big freeze, after the last quantum fluctuation has decayed, eventually, across timescales so vast they require nested exponentials just to write down, the system should return to something resembling its current configuration. Not the same universe. Something close enough to be indistinguishable by any internal measurement. The timescale for a Poincaré recurrence of our universe has been estimated at 10 to the power of 10 to the power of 10 to the power of 56 years. That number cannot be visualized. It cannot be analogized. It is not a really long time. It is a duration so far beyond anything our intuitions can process that the entire lifetime of the current universe is, by comparison, not even a rounding error. Roger Penrose has proposed a cosmological model called conformal cyclic cosmology, the idea that when the universe reaches maximum entropy, reset becomes possible because massive particles no longer exist. Without massive particles, there is no physical basis for a concept of time or scale. The geometry of that ultimate state is, Penrose argues, conformally equivalent to a new Big Bang. The end of one aeon becomes the beginning of the next. He claims to have identified faint signals in CMB data, concentric rings of temperature variation, as signatures of previous eons bleeding through into ours. And then there is the possibility that we are already living on borrowed time of a different kind, that the vacuum state of our universe is not the true ground state but a metastable, false vacuum. If so, somewhere in the universe, right now, there is a non-zero probability of a quantum tunneling event nucleating a bubble of true vacuum. Inside that bubble, the laws of physics are rewritten. The bubble expands at the speed of light. There is no warning, no detection, no survival. It simply arrives, and everything that was is instantaneously replaced by something with different physics. We would never know. The flip side of this is that true vacuum could, in principle, support new structures, new universes nucleating within it, new cycles of complexity. The end of our physics does not necessarily mean the end of all possible physics. I have to tell you something about writing that section. There is a moment, it tends to happen late at night, when you genuinely cannot be certain whether the thought you are currently having is the product of a functioning mind that has existed for decades, or whether it is a quantum fluctuation that arose a millisecond ago, complete with the false impression of having thought everything that came before. That is not a crisis. It is what it feels like to take physics seriously. And I think those ideas matter not because they are terrifying, but because they push on the deepest question available to us: what does real even mean? Which brings me to what I think is the most important part of everything we have covered today. The universe is falling apart. Dark energy is winning. Entropy is increasing. Whatever ending awaits, freeze, rip, or something we cannot yet model, it is coming. And yet here, at this specific moment in a 13.8 billion year history of everything, something extraordinary is happening. The dark energy value in our universe sits within a window of extraordinary narrowness. If the cosmological constant were even slightly larger, the expansion would have been so rapid in the early universe that matter could never have clumped into stars and galaxies. There would be no supernovae, no heavy elements forged in stellar cores, no carbon, no chemistry, no life. If the constant were negative, the universe would have recollapsed into a big crunch before any complex structure could form. The window in which something like us can exist, in which the universe can produce observers, is precise to a degree that is, by any reasonable measure, astonishing. The carbon in your body was manufactured in the nuclear furnaces of dying stars. The calcium in your bones was scattered across space by supernova explosions. The iron in your blood was produced in the final moments of massive stars collapsing. You are not in the universe. You are the universe, at one particular configuration of complexity, a configuration that can look outward and ask about the structure of the whole. Carl Sagan said that we are a way for the cosmos to know itself. This is not poetry. It is a precise physical description of what is happening when you process the information in this video. The universe produced matter, which organized into stars, which synthesized elements, which assembled into planets, which developed chemistry, which gave rise to biology, which generated nervous systems complex enough to model the behavior of the universe itself. You are the most elaborate self-referential structure that 13.8 billion years of physical law has produced. And we are doing this at the right moment. The cosmic microwave background is still visible. Our instruments can still read the light from 380,000 years after the Big Bang. The signature of the Big Bang is still accessible. Other galaxies are still within our observable horizon. The evidence for everything we know about cosmic history is still present and measurable. A civilization arising 100 billion years from now, after most galaxies have retreated beyond the observable horizon, would look out at a nearly empty sky with no evidence of the Big Bang, no reason to hypothesize expansion, no access to the data that allows us to model dark energy. They would have a fundamentally impoverished physics not because they were less intelligent, but because the evidence would be gone. We have a window. It is open right now. And we are using it. The James Webb Space Telescope is the most vivid expression of this fact, a species on one ordinary planet around one ordinary star in one ordinary galaxy building an instrument capable of seeing 13.4 billion years back through time and using it to probe the nature of the force that will ultimately determine the fate of the entire cosmos. There is nothing in 13.8 billion years of cosmic history that resembles this. It is unprecedented and unrepeatable. And I want to say something that might sound strange coming from a science documentary. The real point of understanding dark energy, not the academic point, not the research agenda, is this: it is nearly impossible to sit with this knowledge and continue treating the small scale of human conflict, human anxiety, human permanence, as if it were the default frame. Not because those things are insignificant, but because the frame shifts. The extraordinary thing is not that the universe will end. The extraordinary thing is that you are here, in this window, capable of knowing that it will. That you can sit with that knowledge and find it interesting rather than paralyzing. That is the universe doing the most complex thing it has ever done in its entire history. Now let's talk about what comes next. Because the response to discovering that the universe is falling apart is, characteristically, to build better instruments. The Dark Energy Spectroscopic Instrument, DESI, is currently constructing the largest three-dimensional map of the universe ever assembled. It will ultimately measure the precise positions of 40 million galaxies, tracking the expansion history of the cosmos across billions of years. The full dataset is expected by 2026. If that data confirms the hints from the 2024 results, that dark energy deviates from the cosmological constant at greater than 5 sigma confidence, it will be one of the most significant scientific discoveries in history, immediately reshaping the theoretical landscape of fundamental physics. The European Space Agency's Euclid telescope, launched in July 2023, is surveying 1.5 billion galaxies using two independent probes of dark energy, weak gravitational lensing, which measures how dark matter and dark energy bend light from background galaxies, and baryon acoustic oscillations, which use the characteristic scale of density waves from the early universe as a standard ruler across cosmic history. First results were released in 2024. The full survey completes around 2030, with a target precision on the dark energy equation of state of approximately 1%. The Vera Rubin Observatory, conducting what is called the Legacy Survey of Space and Time, is preparing to photograph the entire southern sky every 3 nights for 10 years. Billions of galaxies. Millions of Type Ia supernovae. The statistical power of this survey for dark energy science is almost incomprehensible. Individual measurements will be less precise than Webb or Euclid, but the sheer number of data points will allow statistical analyses that no previous survey could attempt. Further out, the Einstein telescope, a proposed third-generation gravitational wave detector, projected for completion around 2035, will measure the Hubble constant through an entirely independent method, the detection of gravitational waves from neutron star mergers, combined with optical identification of their host galaxies. This approach has no electromagnetic systematic errors, no distance ladder assumptions. It is a completely orthogonal measurement. If gravitational wave cosmology gives a Hubble constant consistent with either 67 or 73, it will be decisive. What I find genuinely hopeful about this roadmap, and I mean this, is not that we are going to get all the answers. It is that the questions are getting better. More specific. More testable. More discriminating between competing models. That is not the same as progress toward a final theory. But it is progress toward clarity. And clarity about what we do not know is exactly as valuable as discovery of what we do know. We are asking the most precise questions about dark energy that have ever been formulated. The answers, or the refined confusions, will arrive within the decade. Let me bring everything together now, because we have covered a significant amount of territory and you deserve an honest accounting. What we know with genuine confidence, the expansion of the universe is accelerating, confirmed by multiple independent lines of evidence and recognized by the Nobel Committee in 2011. Dark energy makes up approximately 68% of the universe's total energy content. Our observable universe is shrinking, the number of galaxies with which we can, in principle, communicate is decreasing as dark energy pushes them beyond our causal horizon. Dark energy density appears approximately constant, though the precision on approximately is the central open question of observational cosmology. We entered the dark energy-dominated era roughly 5 billion years ago. What we do not know, what dark energy physically is, at any fundamental level. Whether it is truly constant or whether it is a dynamic field. Whether the universe ends in heat death, in catastrophic ripping, or in some scenario current models have not yet conceived. Why dark energy has the precise value it has. And what the Hubble tension is telling us, whether it points to new physics, to early dark energy, to modifications of general relativity, or to something no current theory has captured. Here is the reframe I want to offer. Not knowing, in this context, is not the same thing as failure. The state of cosmology in 2024 is not ignorance, it is the richest, most precise, most productively confused moment in the history of the field. The questions are sharper than they have ever been. The instruments are more capable than they have ever been. The data is accumulating faster than at any previous point. This is what the threshold of a paradigm shift looks like from the inside, not clarity, but the productive pressure of well-defined contradictions demanding resolution. The universe falling apart operates on timescales that utterly dwarf anything biologically relevant. The human relationship to this knowledge is not one of urgency about cosmic events. It is one of orientation, understanding where we are in the story, what kind of moment this is, what is actually short-term versus what is actually long-term. I've made this video 3 times in my head before actually making it. Every time I got to this point, I wasn't sure what the right conclusion was. I'm still not completely certain. Some things resist clean resolution, and the fate of the universe, mediated by a force we cannot identify, is among the most resistant. But I think that is fine. Perhaps the right response to dark energy is not an answer. Perhaps it is a better relationship with the act of asking. In this space documentary, we stepped into the darkest energy in the universe, and discovered that the force pulling everything apart might be the same condition that made consciousness, and curiosity, and this very moment possible. The universe is not simply expanding. It is falling apart. And we are, right now, the most extraordinary configuration it has ever produced in the process of doing so. 13.8 billion years. One species. One window. And we chose to look up. If this shifted something in the way you think about where we are in the story, if you're sitting with that particular feeling of something having rearranged itself, drop it in the comments. This is the kind of conversation that deserves to keep going. Next time, we're going to tackle the question that dark energy raises but cannot answer: if the universe had a beginning, what came before it? The answer, from both physics and some of the strangest mathematics in existence, is more unsettling than anything we cover today, and I cannot wait to take you there. Looking back at everything we've covered, I want to sit with you for just a moment longer, because there is one thing I haven't said directly, and it might be the most important thing in this entire documentary. We spent nearly an hour talking about dark energy as if it were something happening out there, at the edges of the observable universe, in the cold geometry of spacetime beyond any galaxy we will ever visit. And in one sense, that's true. The big freeze is happening out there. The recession of distant galaxies is happening out there. The slow thermodynamic leveling of the cosmos, that is a process measured in timescales so vast that the current age of the universe is barely a rounding error. But here is the thing that stops me cold every time I think about it too carefully. Dark energy isn't just in the distance. It is here. Right now. In this room. In the space between your hand and the wall. It is the property of spacetime itself, not a substance poured into the gaps between galaxies. The vacuum of space in front of your face right now carries the same energy density, approximately 6.9 times 10 to the negative 27 kilograms per cubic meter, as the void between the Virgo cluster and the Great Attractor. The reason it doesn't tear your molecules apart is purely a matter of scale. At human scales, gravity and electromagnetism dominate so completely that dark energy is irrelevant. But it is there. It has always been there. We just didn't know to look for it until 1998. That realization, that the force responsible for the eventual disintegration of all cosmic structure is already present in every cubic centimeter of the universe you inhabit, that is the thing I keep coming back to. Not with dread, exactly. With something more like vertigo. And this is where I want to break something, because I've been speaking to you this entire time as if I have a comfortable distance from these ideas. I don't. I find dark energy genuinely unsettling in a way that most topics in cosmology don't quite reach. Black holes are dramatic and strange, but they are things, objects with properties you can describe. Dark energy isn't an object. It isn't a field you can point to. It is a characteristic of emptiness itself. It is the ground state of reality having a non-zero energy, a fact so strange that when Einstein first accidentally predicted it and then removed it from his equations, he called it his greatest blunder. And then it turned out he was right the first time, for reasons he never imagined, and the implications are more radical than even he would have been comfortable with. I have read the papers. I have talked to people who work on this full-time. And the honest answer, which the most serious cosmologists will give you if you push them, is, we do not know what dark energy is. We know what it does. We know it with extraordinary precision. But its fundamental nature, whether it is a property of the vacuum, whether it is a field, whether it is an artifact of some deeper theory we haven't built yet, that is genuinely, profoundly open. The smartest people in the field are not holding out on you. They are working at the edge of something that has not yet yielded. And there is something clarifying about that, if you sit with it. We live in a culture that is deeply uncomfortable with admitting the limits of knowledge. Somewhere along the way, I don't know, became something to apologize for rather than something to inhabit productively. But the history of physics is not a story of smooth accumulation toward a final answer. It is a story of confident models being shattered by observations that didn't fit, followed by periods of genuine confusion, followed by new frameworks that reframed not just the answer but the question itself. Newtonian mechanics described gravity as a force acting across empty space, instantaneous, universal, precise. It worked extraordinarily well for over 200 years. Then it failed at the perihelion of Mercury, and Einstein replaced it with a model in which gravity is not a force at all but the curvature of spacetime. The question didn't just get answered. The question got replaced. Quantum mechanics did the same thing to classical physics. The assumption that particles have definite properties, position, momentum, independent of measurement turned out to be not just wrong but wrong in a way that required rebuilding the entire conceptual framework. The new framework is not an extension of the old one. It is a different kind of description of reality entirely. Dark energy feels, to many physicists, like it might be that kind of moment again. Not a gap to be filled within the current framework, but evidence that the current framework is missing something structural, something about the nature of space, time, energy, or perhaps the relationship between quantum mechanics and gravity that we have not yet succeeded in reconciling into a coherent theory. The fact that dark energy exists, that the vacuum has energy, that this energy is driving acceleration, that this acceleration is self-reinforcing, sits precisely at the intersection of the two great unfinished problems in fundamental physics, the cosmological constant problem, which is a quantum field theory problem, and the problem of quantum gravity, which is the unification problem that has resisted every attempt since the 1930s. Dark energy doesn't just point to one open question. It points to the place where the two biggest open questions in physics collide. Which means, and this is the part one find almost unbearably interesting, that understanding dark energy might require a theory of quantum gravity. It might require understanding what spacetime is at the Planck scale, below which our current mathematics breaks down entirely. It might require understanding why the cosmological constant has the value it has, which, recall, is 120 orders of magnitude smaller than naive quantum field theory predicts. Explaining a discrepancy of 120 orders of magnitude is not a calibration problem. It is a sign that something in our foundational understanding is deeply, structurally incomplete. Some physicists believe string theory contains the framework to explain this. Others think loop quantum gravity is closer. Others are working on entropic gravity, emergent spacetime, modifications of general relativity at cosmological scales. The field is genuinely plural right now, not in a chaotic way, but in the way that a discipline looks when it is hunting for a paradigm shift and has not yet found it. What the James Webb Space Telescope, Euclid, Vera Rubin, and the Einstein telescope are providing is not just better measurements of dark energy. They are providing the observational pressure, the data that will eliminate some of these competing frameworks, force revisions in others, and eventually compress the possibility space down to something testable and falsifiable. That is how physics actually works. Not from pure theory alone, not from observation alone, but from the productive collision between them. We are currently in the collision. The sparks are visible if you know where to look. Here is what I want you to carry away from this documentary. Not despair about the big freeze or the big rip. Those are so distant in time that they belong in a different category of concern than anything in human experience. Not anxiety about living inside a force we don't understand. Dark energy is not hostile. It is not anything. It is a property of space, and not frustration at the incompleteness of the picture. What I want you to carry away is this: right now, in the early 21st century, we are living through a moment in which the universe's own structure is actively resisting our attempt to understand it. Not because the universe is complicated beyond comprehension, although it is complicated, but because we are asking questions at the genuine boundary of human knowledge, with instruments that have only recently become capable enough to provide real constraints. The boundary is moving. It is moving because of people who dedicated their careers to building detectors, processing data, refining theoretical models, and asking better questions. You watched a 1-hour documentary about dark energy. That puts you in a genuinely small fraction of the human population that has engaged seriously with what the universe is actually doing on its largest scales. Not because this knowledge is inaccessible, it isn't, as you've just experienced, but because it requires sitting with uncertainty, which is an acquired taste. The universe is 13.8 billion years old. It has been dark energy dominated for roughly 5 billion of those years. It has existed in its current form, with stars, galaxies, complex chemistry, for perhaps 10 billion years. Intelligent life capable of asking questions about dark energy has existed for, conservatively, a few 100,000 years. The ability to measure dark energy has existed for less than 30 years. We are extraordinarily new at this. And yet here we are, understanding, with real precision, in real mathematical detail, the mechanism by which everything that exists will eventually be pulled into silence. That is not a small thing. That is one of the most remarkable cognitive achievements in the history of any kind of mind anywhere in this universe, as far as we know. The universe doesn't owe us understanding. It doesn't owe us time, or structure, or the conditions that made biology possible, or the particular arrangement of physics constants that allows stable atoms, stable stars, and stable DNA. All of that could have been different. Most arrangements of the constants would not have produced anything you could describe as complex. We are in a narrow corridor of possibility, and inside that corridor, dark energy happens to have the value it has, which is small enough that it didn't prevent galaxy formation and large enough that it is now, only now, beginning to dominate. If it had been larger, the universe would have been torn apart before the first galaxy formed. If it had been smaller, or negative, the universe might have recollapsed before complex chemistry emerged. The value we measured is, in some sense, the value that permitted us to be here to measure it. Whether that is profound or simply an observational selection effect, whether it means anything or is just the inevitable perspective of observers who exist precisely because the conditions permitted them, is a question I genuinely do not know how to resolve. Neither does anyone else. And I have decided that I am fine with that. Dark energy is pulling the universe apart. Slowly, invisibly, with a patience that makes geological timescales look frantic. And we, this brief, improbable, unreasonably curious species, figured it out. In one generation. Using light that traveled for billions of years and arrived on a Tuesday into a detector somebody built in a mountain in Chile. If that doesn't make you want to look up tonight, I'm not sure anything in this documentary could. And honestly, that might mean you and dark energy have more in common than you think, because the one thing dark energy definitely does not do is look up. So the next time someone tells you the universe is expanding, smile, nod, and think to yourself, yes, it is, and that expansion is the quietest, most patient act of destruction in the history of everything, and we only discovered it 26 years ago, and we still don't know what's driving it, and the telescopes running right now are sending back data that will reshape the answer within your lifetime. That's not an expanding universe. That's a universe in the middle of something. And we are here, somehow, alert enough to notice. If this documentary changed how you see that patch of dark sky between the stars, the part that used to look like nothing, then share it with someone who still thinks nothing is there. Because the most unsettling discovery in the history of cosmology deserves at least one more set of eyes looking up tonight, wondering what the silence is actually made of. The sections still unwritten according to the outline are Hook, parts 1, 2, 3, 5, 7, 8, 9, 10, and the closing CTA. However, the last written paragraph provided ends with what is clearly the CTA/outro. The instruction is to write 966 words continuing directly after that final paragraph. Given that the script has reached its natural conclusion and the CTA is already present, the only logical interpretation is that earlier sections, Hook through part 3, and parts 5, 7, 8, 9, 10, were never written, and what exists are parts 4, 6, the summary, and the CTA. The 966-word continuation should therefore fill in missing narrative content that would logically precede what's been written, but since the instruction says, "Vit tip ngay, write forward," I will continue forward from the CTA with content that expands and deepens the closing reflection, then delivers the final end beat. There is one more thing worth saying before we close this out, and I debated whether to include it because it sits slightly outside the lane of what a space documentary is supposed to do. But here we are, so. The history of cosmology is not a clean progression from ignorance to enlightenment. It is a series of confident frameworks colliding with inconvenient data, producing crisis, producing revision, and occasionally producing genuine paradigm shifts. The geocentric model was not replaced because someone had a better idea sitting in an armchair. It was replaced because observations accumulated that the old model could not absorb without becoming ridiculous. The static universe was not abandoned because Einstein or de Sitter thought it was philosophically unsatisfying. It was abandoned because Edwin Hubble pointed a telescope at Cepheid variable stars in distant nebulae and the redshift data was simply not compatible with anything staying still. The steady-state model, which had genuine elegance and serious proponents into the 1960s, was not defeated by argument. It was defeated by the cosmic microwave background radiation, discovered accidentally by two engineers testing a microwave antenna in New Jersey who kept finding a persistent signal they initially attributed to pigeon droppings. The universe does not care about our aesthetic preferences for our models. It just keeps producing data. Dark energy entered the picture the same way every previous paradigm shift entered, through data that refused to cooperate. In 1998, two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were measuring the distances and recession velocities of Type Ia supernovae, which function as what cosmologists call standard candles, sources of known intrinsic brightness that allow distance calculations across enormous scales. The expectation was that they would confirm the deceleration of cosmic expansion. Gravity, after all, should have been slowing things down since the Big Bang. Instead, both teams found that the most distant supernovae were dimmer than expected, meaning farther away than the models predicted, meaning the expansion was not decelerating at all. It was accelerating. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the Nobel Prize in Physics in 2011 for this discovery. But the prize almost understates what happened. What happened is that two independent groups of astronomers, expecting to confirm existing theory, instead found evidence that something they had no name for was pushing the universe apart faster and faster. They did not celebrate. By multiple accounts, both teams spent weeks checking for systematic errors before accepting what the data was saying. That is not a dramatic failure of confidence. That is how science is supposed to work. You resist your own findings until the resistance becomes unreasonable. And eventually, it became unreasonable. What they had found would be named dark energy. The name is a placeholder for our ignorance, not a description of what it is. It is dark because it does not interact with light. It is energy because it has the effect of energy on space-time geometry. Beyond that, the name tells you nothing about its nature, its origin, or its ultimate behavior. 26 years later, we are still using the placeholder. The placeholder has survived every observational test applied to it. And that itself is worth sitting with. The most powerful force in the universe is described by a label that essentially means, we found this, we measured it, we have no idea what it is, and we named it accordingly. This is actually more common in physics than the polished textbook version suggests. The electron was named before anyone understood its quantum mechanical behavior. Quarks were named with terms borrowed from a James Joyce novel, up, down, strange, charm, bottom, top, because the people who discovered them understood that the names were temporary handles for mathematical entities, not descriptions of physical reality. The Higgs boson was called the God particle by a publisher who wanted a more marketable title and has been quietly resented by physicists ever since. Naming in physics is often an act of provisional labeling while the real work of understanding continues underneath. With dark energy, the real work of understanding is ongoing at every major observatory on the planet and several above it. The Euclid satellite launched in 2023 and is mapping the large-scale structure of the universe with a precision that will constrain dark energy models in ways previously impossible from the ground. The Vera Rubin Observatory in Chile, when it reaches full operational capacity, will catalog tens of billions of galaxies and track weak gravitational lensing across cosmic time, another method of measuring how dark energy has shaped the distribution of matter throughout the universe's history. The Nancy Grace Roman Space Telescope is designed in part to conduct the largest survey of Type Ia supernovae ever assembled, extending the original measurement that started all of this in 1998 out to distances and redshifts that were completely inaccessible to the original teams. We are not at the end of this story. We are at the point in the story where the detective has assembled the evidence board, identified the major suspects, eliminated several of them through careful questioning, and is now waiting for one final piece of information that will make the pattern clear. The next decade will provide that information. Whether it confirms the cosmological constant, reveals a dynamic field, or points to something that requires modifications to general relativity at cosmological scales, we do not yet know. But we will know. Within the lifetime of most people watching this, the question of what dark energy actually is will have a substantially better answer than it does tonight. And when that answer arrives, in a paper, in a press conference, in a Nobel Prize announcement that interrupts the regular news cycle for approximately 48 hours before the world moves on, remember that you were here, in the middle of the uncertainty, when the data was still coming in and the universe had not yet decided to explain itself. That is not a small place to be. That is exactly where all the interesting things happen. If the universe does decide to explain itself, and the data suggests it is already beginning to, the explanation will arrive not as a single thunderclap but as an accumulation. A measurement here that slightly tightens a constraint. A galaxy survey there that rules out one more model variant. A spectrum from James Webb that shows something unexpected in the light of a galaxy 11 billion light-years away. The picture sharpens incrementally, and then one morning someone runs the numbers and realizes the picture is already sharp enough to read. That is the honest ending to this story. Not a dramatic revelation, not a moment where physics stops being strange, but a gradual clarification of something that has always been there, operating across every cubic centimeter of space, in every direction, at every moment since the universe was roughly 5 billion years old and dark energy finally achieved enough leverage to overcome gravity's resistance and begin accelerating the expansion we now measure as a fact of cosmological life. The universe is not trying to terrify you. It is not indifferent in any personally hostile way. It is simply vast, and old, and governed by rules that took us most of human intellectual history to begin reading correctly. We have been reading for about 400 years with instruments, and about a century with instruments good enough to reach beyond our own galaxy. In that time, we discovered the expansion. We discovered the acceleration. We measured the background radiation of the Big Bang itself. We detected gravitational waves from colliding black holes more than 1 billion light-years away. We imaged the shadow of a black hole's event horizon. We collected light from the first galaxies. All of this in roughly 100 years of serious observational cosmology. The next 100 will be at least as disorienting. Probably more so. Because the tools are better now, and the questions are more precisely formed, and the gap between what we can measure and what we cannot has never been narrower. Dark energy will not stay mysterious forever. The universe has never, in the long run, successfully hidden anything from a species that kept looking. So keep looking. And the next time someone asks you what dark energy is, tell them the honest answer: it is the dominant component of the universe, it is accelerating the expansion of space, it may be the cosmological constant Einstein introduced and later doubted, it may be something stranger, and we are, right now, in the middle of finding out which. That is not a gap in human knowledge. That is the frontier. And there is no more honest place to stand than exactly at the edge of what is known, looking out into what is not, knowing that the edge itself is moving.